Hello everybody, my name is Adi Pai and I am a person in Mr. Bukta's class in 2024 making this video to discuss double integrals and volume. Just generally a basic overview of what they are, what they're used for. We're going to go through some examples from the textbook, we're going to go through some basic problems, we're going to discuss how they help us, what you can really do with them, and just a basic overview and intro to that side of math. So, we're all very familiar with the standard integral, right? So let's just like make a quick comparison. Try to look here, integral, and we'll call it, this is our single integral. It's like a standard, everyday, that type of thing. Sorry, my voice is a little bit gone, so I'm sorry if I sound a bit muffled, but essentially, your standard integral looks something like this. If you have let's say you have a function on this axis, and your function looks something like that, like some sort of sine wave type thing, your integral is essentially going to be calculating the area between this curve and that curve, like the area between the x-axis and, or it could be the y-axis, the area between an axis and the curve. And when you do that out, you're going to get the area of this shaded region right here, right? And we know this. We did this in BC, we did this in multi, we've gone over integrals many times, and we're very familiar with them, which is actually pretty good because this is pretty similar. So this is really useful for finding things like position from velocity functions and finding velocity from acceleration and all sorts of other things like that. But there's one limitation, and that is you need to use two variables and only two variables in single integrals. You have your x and you have your y, and that's basically it. And when you're integrating with respect to just x. Like there's no, this function is only with respect to x, right? Like there's no other variable being considered except for x. So that limitation is the reason why we don't use single integrals to find, say, volume, unless it's like, volumes of revolution like in BC. There's some scenarios where you would, but generally speaking, you don't really use a single integral to find anything greater than a 2D result, like area. But let's say you wanted to find the volume between... Now, I'm not the best artist, so this might be a little bit of a weak drawing, but we're going to see how it goes. This is our 3D x, y, z, a 3D coordinate plane. And let's say, here we go. We have a sphere, basically. That wasn't too bad. So let's say we have our sphere that is essentially that's enclosing this area, and it looks something like, like that, sort of. Like this segment is, what is that, 1/8? Yeah, 1/8 of a sphere. And it's bound by the x, y, and z plane. And let's just say you wanted to calculate the area of that entire sphere, the area in between that sphere and above this plane, the xy plane. So you want to figure out the area that is going up from here and bounded by, from the top, this upper curve. So how would we go about finding that? Now, it looks a bit annoying at first glance because, there's more variables involved, but it's really not that bad. It's pretty similar to how you solve one of these things, except you're just considering one extra variable, and while that may sound intimidating, we actually prepared for this really well with our iterated integral stuff that we did last video. So we're going to just use that essentially to figure out how this is done. So before we actually go into the simpler method of our double integral, we're going to quickly discuss the approximation way, which is not going to be used too frequently because, it's an approximation, but it is important to discuss. And the way that would work is very similar to how you do it in a normal integral. So in your regular integral, we did something like this. For each, so integral as well, like it's whoops, that's the wrong pen. An integral is using dx, so it's using infinitely thin slices of x. So that looks like this. You have little boxes here that are all accumulating to go up and touch that curve, and when you put them all together, You get the idea. But when you extend these boxes outwards like that, and you keep them going from your left bound to your right bound, you create a rough approximation of the area under the curve. And this was our Riemann sums, right? Like we did this in BC a lot. And you'd have your midpoint sum, your left end, your right end sum. Like, there's all the methods you can use to approximate. Now, this is considering one variable, right? Because you're varying essentially the height is changing, but the thickness is remaining constant. And that delta x, that thickness, is approaching 0 as you go from a summation up to your integral, right? So the integral is essentially an infinite number of slices with thickness 0. And what we're going to do for this is a very, very similar process, except now we have a 3D object, right? Not a 2D object. And the difference that comes with the 3D object is we're going to do little prisms instead of rectangles. So whereas we just do rectangles here, we're going to consider two different things here. So the way this works is we have two variables, y and x, and then z is generally expressed as a function of x and y, right? So if z is that, we're going to replace z with saying, we're going to say z is just, z is equal to f of x comma y. And let's see if we can figure out the same method here. So where in this scenario, our dimensions are going to be x and f of x, right? That's the dimensions of the rectangle. It's going to be x wide and f of x tall. With this one, we know the height is going to be z, and z is what? F of x of y. So the height of this prism is going to be f of x of y, and the width, well, that's just going to be x and y, right? The width, the two other dimensions are going to be those two. So what you get is, you get this, okay, that's the wrong tool. You get a little rectangle here, essentially, and that prism, sorry, I misspoke, stretches up to, oh god, let me change color so it's a bit more visible. Yeah, Mr. Bookta has a hard job, guys. Like, this is tough to draw. As you go up to here, you're essentially going to get a little rectangle that looks something like that. And that's going to be reaching up to a point, like this point here. Usually use the midpoint, like whereas in Riemann sums, usually the midpoint is like the most accurate method, right? So same with this. You want the midpoint to be contacting the sphere, the surface of the sphere. And what you get there is essentially a bunch of slivers that look something like what you're used to with the Riemann sums from last year, but instead you're now going to get a three-dimensional, prism that reaches up to the top of a sphere instead of a curve. Or surface, not a curve. So, yeah, it's going to be the same sort of process, though. You're going to have infinitely thin little slices, except instead of slices, this time you're going to get little, they're like French fry shaped almost, basically. It's a bit of a weirder look to them. But yeah, you're going to get, this is a really bad drawing, but you're going to get the idea. It's going to be little sticks, essentially, that stick up. And if we zoom in on one of these, I'm going to draw on the side here. If we zoom in on one little column, yeah, we'll go with that. It's going to be, we're going to go with the height first. The height we know is going to be our z value, and z is just going to be f of x, y. And because it's going to be at a specific point, we're going to just call it, x sub I, y sub I. And then the width here is going to be our delta xi. And this width, this length, I guess, is going to be delta yi. And if you take this, you can kind of combine them to make the base by multiplying them. That's just, we're going to call that base, it's going to be xi times yi. We're just going to call it delta ai. So yeah, this rectangle's area is thus going to be, this rectangular prism's area is thus going to be a sub I times f of x sub I, y sub I. So yeah, essentially the way a double integral works in principle, just to give you a basic idea of what it would look like, it's very similar to this, just expanded to a second variable. And yeah, it's literally just instead of doing rectangles, you're going to do prisms, and it's the same thing. You're summarizing. You're summing up. That's the word. You're summing up these little shapes to create a bigger continuous solid. And it's called the definition, but as you get more and more shapes, the thing will become essentially smooth, and at that point, you're going to get our proper double integral that is going to have, no actual like a thickness of 0 effectively at that point. So let's use this to examine what a double integral actually is. So we see here that what this is really doing, like the area of one prism is this. It's f of x, y times, I'm just going to do the full star symbol, times our delta a. F of x I, y I, times delta ai. Yeah, and then if we want to convert this to our double integral, it's not too bad. So we're going to express it first in the general form of the integral. So we're going to say the double integral over the region R of f of x, y, dA, because you're integrating over an area, is equal to basically this summed up an infinite number of times. Because, the way the integral works is you're getting infinitely thin slices and an infinitely high number of these thin slices, and you're adding them up to create a finite object. So when you put that into notation, it looks something like this. So you're going to get the limit as the difference, which is delta. I remember the magnitude of that. Delta tends to 0. We're going to do our fancy sigma notation for summation of, we're going to put n at the top because it's an n number of intervals, and our counter I is going to be equal to 1. And it's going to be of f of x sub I, y sub I, times delta a I. And that, right there, is our definition of a double integral. So when you do, later on in this video, we're going to do the actual math out, you're actually doing this. This is literally it. This is the official definition of what a double integral actually is, and henceforth, even though we're going to take some shortcuts to make it a bit simpler, that is actually what it's doing. Now, this same thing right here, oh god, iPad moved. This block right here is also equivalent to the volume. So it's going to be, that represents a 3D thing. So it's going to be the volume of a solid region that is above that constraint here, that R, and below our f of x, y. And what that really means is, going back up to here, our R was this yellow outlined plane at the bottom, and f of xy was that shape. So yeah, it's going to be the volume underneath your function, which is going to be f of x comma y, and the volume above your your domain, your thing, your, what's the word for it, your region, your plane region, that's the word. So yeah, that is essentially what a double integral really is, and the properties are very, very similar. I'm not gonna go over them in complete depth because they're in the textbook, and they're very, very intuitive. It's like when you have a constant in the double integral, you can take that out the same way as a regular integral. What's the next one? You can add, and you can, if two things are added inside, if two functions are added inside a double integral, you can separate that into two double integrals. If a function is above 0, is greater than or equal to 0 at all points in the interval, the double integral of that function will also be greater than or equal to 0. Same thing applies if it's a function instead of 0, and then lastly, there's one more. Yeah, if your plane region R is the union of two subregions, you can add those subregions up separately and take the double integral of those two subregions on a separate page, and then add those together to get the total area, the total volume, of that full region. So yeah, that is, I explained that pretty poorly, but it's in the textbook pretty much like on the first page of that chapter. So if you need more information about that, please check that out, because I did not explain that very well. But yeah. Next, we're going to go over another quick example about how to actually evaluate a double integral. And this is going to be quite similar to how we used iterated integrals in the past. So you'll find it's pretty familiar and not too terrifying to do. So that's the good thing. Now, if we're going to evaluate an integral, let's do one. Let me find a good example. Hang on. Let's see. Sure, we can do this one. So typically the first step when you want to solve any double integral is you want to rewrite it as an iterated integral, right? Because when you see this, it's a bit tougher to solve. Like this, we don't really know how to solve this as it is. So if you take this and you convert it into, say, this, and you make dA into dx dy, this is very solvable, and this makes us happy. We can solve that. So we're going to go over a quick theorem now that lets us do exactly that. And this was invented by, or maybe named after, a guy named Fubini. And I don't really know who he was, what he was up to, but he has a pretty cool theorem that we like to use in multi. So let's go over his theorem real quick. So this is Fubini's theorem. Let's just pretend that person is Fubini. Anyways, let's just say that you have a function f of xy, and it's continuous on some plane region R. So let's just say function f of xy continuous on R. Now let's just say if R is defined by, so R is a plane region, right? So that's going to basically mean that it has one of its two variables can be defined with literal numbers, and the other variable can be defined as a function of that first variable, because it's a plane. So what I mean by that is you can basically define R by, let's say, A is less than or equal to X is less than or equal to B, where A and B are both numerical constants. And then you can also say and G sub 1 of X is less than or equal to Y is less than or equal to G sub 2 of X. And what this means is because it's a plane, you can express one of the two variables in terms of a function of the other. So in this form, we basically get R defined in terms of basically just X. And that makes it a bit easier for us later on, as you'll see when we evaluate our integral in our example. Okay, and what this basically means is if this is true, then we're allowed to take a quick shortcut. And that shortcut looks like this. So if we have our double integral over R of f x y, and remember it's dA, that is effectively the same as taking the iterated integral from a to b here, and then g sub 1 of x here, g sub 2 of x here, of f of x y dy dx. And yeah, it's a really nifty theorem that's really useful for a lot of what we do. This part here, like this is a bit annoying to solve. We don't know the math necessarily. Well, we might, but like it's a bit difficult to solve it in that raw form. But when you look at this is much simpler. This is much more easy to process and solve out using techniques we already know from the past chapter and the past video. So we're going to solve it in this way. And by the way, the same thing applies to y. So let's say you have, if r is, I'm going to just change a couple numbers here real quick. Let's just say if you have r is defined by if r is defined by a is less than or equal to y, where'd the pen go? There we go. By c is less than or equal to d of, c is less than or equal to y is less than or equal to d, and h sub 1 of y is less than or equal to x is less than or equal to h sub 2 of y. You can do the exact same thing. This is just transferring it for a different variable, you can just change this out for C and D and this out for, yeah, same idea. Here we have D up top, C on the bottom, H, Y, Y. And you just swap this order. Dx dy. Yeah, so it works the same way for both variables, and that's important to know because sometimes it is actually a lot easier to solve it in the other variable than to solve it in the first one. And that's good to keep in mind. Because occasionally you're going to look at it one way and it's just going to look absolutely horrible, and then you integrate in the other variables like domain, and it's just much easier to deal with. So let's now apply that to a quick example where we where we convert a double integral to an iterated integral. Now, let's just say, hypothetically, we have a integral that looks like this. Let's do the classic EX. And let's say we have to evaluate the double integral over region R of 1 minus 1/2 x squared minus 1/2 y squared dA. And the region R is equal to 0 is less than or equal to x is less than or equal to 1, and then 0 is less than or equal to y is less than or equal to 1. And here, let's just move this up. So, first thing we can do here is draw out our region. And the way we're going to do that is by literally just making a square on a coordinate plane. So this is your standard everyday coordinate plane with two variables, and we have here 1 and 1. Switch to yellow maybe. This square right here is our region R. This entire thing is what we are integrating over. Okay, and when we're looking for essentially our process, we're gonna first look to see whether we think it's easier to integrate with respect to x or y. Now, normally we look at this up here, and then we look for which one is given in terms of numbers. Now, in this case, this is a pretty basic introductory problem, so they're both given in terms of numbers. So here, whether we choose to use dy dx or dx dy, like, it really doesn't matter because they're both numbers, and they're both just given to us at the very start. So it's pretty elementary. We can do either one. Let's just do dx first. So we're gonna do it this way. We're gonna take this entire thing. We're going to just put an arrow right there. Here, let me extend that real quick to include the dA. We're going to take this entire thing, and we're just going to set it equal to 0 to 1, 0 to 1. Let's do dy first, actually. I think that will be a little bit, that's what the textbook does, so I'm just going to make sure that the answers match using that. 1 minus 1/2 x squared minus 1/2 y squared. Is that a function? Yeah, that is our function. And then dy dx. So you see what we just did there? That's basically just what Fubini's theorem is. We took our integral and we just shoved it into the form of an iterated integral by using the bounds given up here and by adding our dy dx at the very end. Because as we established way back here, dA is really just dx times dy, right? So that we did with deltas, but it's the same general idea. Like dA is it's an incremental area, and as we know, area is length times width, and length times width is x times y. So dx dy is dA. So we're really not doing a whole lot here. We're just kind of giving numbers to the raw expression that we got earlier. It's not too bad. It's pretty intuitive, I think, personally. But yeah, it's not too bad. So we're gonna start off with this, and we're just gonna start and evaluate this the standard way that we did last chapter. Now, we're going to plug in our first integral, and we're just going to integrate this inner function with respect to y. And when we get there, we're going to keep this first integral aside as before, and we're going to get 1 minus 1/2 x squared y minus y to the third over sixth, 6. And that goes from 0 to 1. And we still have our dx left over from here. And if we kind of evaluate that out, we're going to bring our integral up again, and we're just going to have 5/6 minus 1/2 x squared dx. And now we literally just have a regular integral, so this isn't bad to solve at all. And when you solve that out, you get 2/3, or you should get 2/3 at least. Let me confirm that checks out. And yeah, that's what the textbook says. So when you evaluate this entire, this looks pretty messy at first. You have, some squares, you have a dA, you have a double integral, but it really works out quite nicely. You just go over here, you use Fubini, you make it into your iterated integral, and then you just plug it in, and you get our nice final number of 2/3. Nice. Let's do one more example. I think would be a good idea. Let's find volume. So this was a bit more abstract, but we all kind of established at the start of this thing that the true purpose of an iterated integral is to find volume. So it'd be a shame if we went through that entire thing and didn't actually solve for volume, wouldn't it? Let's do that. We're going to go and look at this next question, which is going to be example 3 in the textbook. And this is going to be with the EX. And this is going to be to find the volume of the solid region bounded by paraboloid z equals 4 minus x squared minus 2y squared and the xy plane. Right, so we're going to start off by just kind of figuring out our bounds. So this is when you look at this problem, it looks almost deceptively simple. And it is not that bad. When you look at it, it just says find the volume between this thing and this thing. Now, we've been finding volume since like elementary school, right? This shouldn't be too bad. And it's not. It's just we need to use a double integral to do it this time because it's a really weird kind of amorphous blob instead of a proper, shape for volume. So let me try and draw this out for you guys first. This is going to be tough. Let that be our z-axis. We're going to go this way for x, this way for y. Actually, let me change that angle a bit. Yeah, that's a bit better. Z, x, y. Get our arrows going. Right, so to draw this out, let's remember that if we put z equal to 0, we get a circle. So that circle is going to look something like this. Right? Yeah, that should be right. And then from there, we're just going to get this dome shape, a series of smaller and smaller circles until we finally get to like a point, maybe around there. So when you draw it out, it's going to look something like that. Yeah, guys, I'm not really an art student. The furthest I've gotten is like drawing for fun. Yeah, that's kind of the vague idea of what it looks like. Like if you shade the God, let's take out the shading. Yeah, I'm not proud of that. But basically, there's a very good drawing in the textbook if you want to look at that instead. But it's essentially this. It's going to be a function bounded above the xy plane. The xy plane, as we know, is this region here, like this entire plane, and the paraboloid, my bad, is going to be that yellow shape there. So our region is going to be filled in with this area right there. That looks like a scribble a first grader would make. But okay, you get the idea. That green blob inside there is the area we're trying to find. And when we actually do that out, it looks something like this. So we're going to start off by figuring out whether we should put our numerical bounds for x or y. When you look at the region, it's a circle, right? So I mean, when you look at it, it's very symmetrical from all sides and even from top or bottom. So it doesn't really make a difference we're just going to set it to x because we can. So we're going to do constant bounds for x and then variable bounds for y. Now, how do we actually go about finding these bounds? Well, if you draw it out and you label these points correctly, we are going to find out that all of these little black tick marks here are going to be at 2 or negative 2. So the maximum value for x, which we're going to decide which we picked is going to be a numerical bound, is going to be 2, and the minimum value is going to be negative 2. So knowing that, we can set our bounds for x. Negative 2 is less than, that's a z. Negative 2 is less than or equal to x is less than or equal to positive 2. And now that we know x, we can solve for y. So our original function was, that. So we're going to say if we let z equal to 0, and then we're going to get, if we do that, we're going to get x squared plus 2y squared equals to 4. And now we're just going to solve for our x. So we're going to go to, solve for y, my bad. So doing that, we're going to get 4 minus x squared divided by 2, and then square root of all that. That should equal y. Oh, sorry, plus or minus. And the reason it's plus or minus is going to be because, y goes from that side to the other side, and it dips into the negative region there, as you can see. So the bounds are going to be that for x, and then for y, you're going to use that thing we just got. It's going to go from negative 4 minus x squared over 2 less than or equal to y less than or equal to positive 4 minus x squared over 2. Can I get a smaller eraser? I guess I can. That didn't really work. 4, that's 1 minus sign, sorry. 4 minus x squared over 2 is our upper bound for y. Perfect. Now we have the bounds for y and the bounds for x, so we can just apply Fubini and solve or create first, I guess, our double integral. So volume, as we know, is the double integral over r of f of x dA. So let's write that down. Volume equals, we established this earlier. And we know from Fubini that we can change that to our bounds. And we decided we were going to use x as our inner function and then y as our outer. Oh wait, no, sorry, other way around. We're going to use y as our inner and x as our outer because x is our numerical bounds. So we're going to set it up like this. Our outer bounds are going to be negative 2 to 2. And then our inner bounds are going to be negative, 4 minus, can I zoom in? No, I can't. 4 minus x squared over 2, 4 minus x squared over 2. And our function, as we mentioned before, is just going to be 4 minus x squared minus 2y squared. And y is our inner, so we're going to put dy here, and x is our outer, so we're going to put dx there. Nice. We have our iterated integral set up, and now we're just going to solve that. So, as you can see, like, this really isn't, the double integral part is kind of short. Like, all it took was, setting up r up here, and then setting up this, writing down this one part. And now we're just on to a problem from the last video. Like this, we've done this stuff before many times. So we're just going to use that to figure out how we can get things to work. So let's start off by doing a quick use of our integration techniques. So we're going to solve out the first integral, and we're going to apply the bounds. And when you do that out, you're going to get negative 2 to 2, because we're going to keep the outer integral. And then on the inside, you're going to have, let's make that a proper bracket, 4 minus x squared y minus 2y to the third over 3. And I really don't want to write that again. 4 minus x squared, I'm just going to do it this way, slash 2. And that's 2 on the top, 4 minus x squared slash 2. Okay. It's a long process, I know, and then dx at the end. All right, let's keep going. Now, we have some things we can take out of this. when you evaluate that, when you plug this in, I'm gonna just do it off screen because it's gonna save some time. When you plug in these big annoying bounds, you end up with a constant which is going to be 4 over 3 rad 2, and if we need to simplify this at the end, we'll deal with it, at the end. We're gonna do multiplied by -2 to 2. What is it? 4 minus. Whoops, I had fell. Inside it's going to be 4 minus x squared, I recall. Yeah, 4 minus x squared to the 3 halves times dx, or with respect to dx, with respect to x. Yeah, that checks out. All right, now we're going to take one other step, and this is going to be to convert it to, instead of x, we're going to do in terms of theta. Why would we do this, you might ask? Well, it's an easier method than leaving it in terms of these things, so we're just going to go with saying x is equal to 2 sine theta. And we've done similar things in BC. You guys should be somewhat familiar with this idea. X is going to equal 2 sine theta, and we do that just because this is an integral that we are not used to solving. It's sorry, that's the word, trig sub, my apologies. So it's something we've done before. It's trig substitution, where we're essentially just swapping out x for, what's the word, for a trig function that is integratable, that we can integrate in a manner that we know. So we're going to say x is equal to 2 sine theta, following the rules of trig sub. And with that in mind, we're going to change our bounds. So by evaluating the new bounds for using the new variables, we end up getting negative pi over 2 to pi over 2. And our inner function just becomes 16 cosine to the 4th theta d theta. And now by taking that out, we can, what can we do? Right, okay, we're going to take out our main thing, we're going to take out our 16, and we also are going to, we know for a fact, we know what cosine essentially looks like. It's, if you look at that interval, it's the same thing as saying 2 times, it's just double, here, I'll show you what I mean. So if we take out the 16, we're going to get 64 over 3 rad 2 times that integral. But the thing about that integral is it's essentially the same thing as this integral, not 16, sorry, times 2. And that's because of the properties of how cosine works. So knowing that, we're just going to take out a second 2 because it's 2 of this. We're going to just do that times 2, and that'll become 128, and we're going to solve that out right here. We're going to do 128 over 3 rad 2, and this is a formula that I don't think we learned this in BC, but I think it's called Wallace's formula. It comes up in this one example. I don't believe it's something we need to know for any test in multi, but it's this neat formula that you can use to figure out the evaluation of cosine to the n theta. And we're going to use that essentially to figure out what this could be. And when you apply that formula and when you figure everything out, you're going to end up with a value for that integral of 3 pi over 6. Over 16, I misspoke. And on a test, I'm assuming you're going to be able to solve that using a calculator. But for the sake of the example, we're just going to do it using that formula. So we get 128 over 3 rad 2 times 3 pi over 16. And simplifying that, you have 4 rad 2, 4 pi rad 2, I think, yeah. Let me rewrite that. 4 rad 2 times pi over 4 pi rad 2. And that is going to be our answer. All right, so what have we learned today as a whole? Let's go over quickly. So when you look at a single integral, it is the area underneath the curve, and your result is going to be a number. And the same as with the double integral, but with the single integral, that number represents the area of a 2D space. And in this case, in all cases, it's the area between a curve and an axis. Usually it's the curve above or below the x-axis and the x-axis itself. And you use that to figure out maybe velocity from acceleration, or position from velocity, or any other something like with the concerns one variable like that. But what you can also do is take a double integral, and it's a very, very similar process. All you're doing is scaling up one dimension, And instead of accounting for the area of a 2D space, you're accounting for the volume of a 3D space. And whereas the integral would be the area underneath a 2D curve, this is the volume underneath a 3D, a 3D surface, in between two 3D surfaces, usually a plane and some funky sphere or ellipsoid or whatever. And yeah, in regular integral, you're going to be doing that by summing up infinitely thin little rectangles. And with a double integral, you're going to be doing that with infinitely narrow rectangular prisms. And that's going to be the dA, or the delta A, that's going to be going towards 0 when you're trying to solve for that. And the other parameter is going to be the height, which is always going to be a function of x comma y, so z, essentially. And when you go about solving that, you're really just doing a summation. I mean, we've seen this before. We've seen summations many times in the past. But what it's essentially going to do is the same as a regular integral. You're adding up all these little points, and when you put it out into this form, it looks like, oh god, it looks like that. So yeah, that's going to be essentially what that does. Okay, next part we need to review is Fubini's theorem, and that essentially is how to convert and evaluate double integrals. You can convert them into a form that you recognize by taking a double integral and giving it a region, and then you can convert that into your standard iterated integral and then solve that the same way you would solve any other iterated integral, which we talked about extensively last video. So that is how you actually evaluate these things. And there's some examples that we went over here about how to find the volume between two regions. If you get your numbers given to you, it's a lot easier. It's very convenient if you get this nice little package of numbers. And if you don't, and you get an equation, it's not that bad either. You just put in a variable bound for one of your variables, so it's not too bad. One last thing I do want to mention, because as we saw here, you use trig sub sometimes to evaluate an integral. I want to quickly review and quickly mention that it is sometimes easier to convert double integrals to a polar form instead of your regular Cartesian. And the reason you do that is because often, or not often, but occasionally, it is simpler to just evaluate it in that form. And the way you'd go about doing that is by doing this. So let's say you have your typical f x y d a. Like that's your regular double integral, right? This is also equal to solve the region R, but you're going to instead do f of, so if we remember from polar, x is equal to r cosine theta, right? And y is equal to r sine theta. So we're just going to do r cosine theta, r cosine theta, r sine theta instead of x comma y. And that's just going to be times dA. But the way dA works in polar is slightly different. So whereas dA in rectangular is dx dy, dA in polar is a bit different. So it's going to be basically, you're doing, you have to add an extra r in there. And the reason that kind of works out is you have to like factor, here I'll show you, I'm explaining it a bit badly. So when you take that, you can take this thing over here, and then you can then say that f r cosine theta r sine theta dA is equal to the double integral for r. Let's give that proper numbers and redraw those integral signs. The integral over, and instead of a and b, we're gonna put some variables here and explain what they are in a moment. Alpha h1 theta beta h2 theta, and the actual function is going to be f of r comma theta times r dr d theta. And this is going to be for a polar, for if f is works, if f is continuous on polar region given by 0 is less than or equal to h1 theta, which is less than or equal to r, which is less than or equal to h2 of theta. And 0 is just to make sure that you're, in a positive area, because polar doesn't really work with negatives as much. And here you have, and also you must also have, this is just your a and b essentially, but it's just fancier because you're in polar and it's angles. Alpha is less than or equal to theta is less than or equal to beta. And then where, one more condition, where beta minus alpha is less than or equal to 2 pi, because you only want to go around one time. That's just for the sake of the integral. Now, there are some good examples about this in the book, so I'm just going to leave those to you, because this video is getting very, very long, and I want to just make sure that it is still digestible. And essentially, just try and make sure that this is a tool that you have, and it's very, very useful at times to save you energy, and sometimes it's the only way to solve a problem, and you learn that the hard way if you don't study this part now. So make sure you know how to convert to polar. That's a very useful skill, and make sure you know when to do it. Make sure that you've met all these conditions, and then if you find that a problem isn't really working out in Cartesian, feel free to explore the polar route and see if that works out better. So yeah, I'll leave you with this for today, and hope you have fun studying and enjoy the test coming up soon.